String theory.
It can lead to revolutionary changes of how you think about the world. If we were able to throw things at each other at the highest possible energy, what we will discover inside everything?
Is that a string that we will discover there?
That predicts everything. It's also important to have a few crazy people. These equations are so complex that they don't have one solution. Each Hanatsuk start becoming smarter and smarter, and then they become sentient one day.
Because we're looking from inside the pond. This is so much to understand and consider. Does it have anything to do with Marvel's multiverse?
Follow the Marvel sequence, but special thing happening as far as what we see the universe today. You don't have enough information to tell why we live in the universe that we live in.
String theory. Can it help us explain things that traditional particle physics can't explain? And what insights does it offer regarding our universe? We are going to have a really interesting discussion about this with physicist Vatche Sahakian. And Team Telecom Armenia is the partner of our interview series about science and current technologies. String theory. I guess everybody has heard this term, but I'm not sure that we really understand what it means. So can you explain the basic principles of this theory and how does it differ from traditional particle physics?
It's a good question. So in physics, generally, there are branches which are directly connected and guided by experiments. And they often lead to applied physics and technology transfer and all that. But a lot of that is also dependent on understanding the laws of nature. How do we see the world? How do we describe it in a theoretical, mathematical framework? So generally in physics, you have experimental and theoretical branches. And string theory falls within theoretical physics, even more so, I would say, theoretical mathematical physics, because it's not directly connected to experiment currently. So the idea is that it's a framework of understanding the laws of nature at a very fundamental level, very sort of foundational. And eventually, once you have that understanding, it will naturally lead to, connection with the real world and experiments. For example, if you look at the branch of theoretical physics and you mentioned particle physics and how it relates to it, particle physics has an experimental and theoretical component. And the experimental component is about building these big accelerators, often to smash particles together to see what are things made of. When you experimentally discover the building blocks of nature, then you explain it with a framework of theoretical particle physics, which is sort of a well-established field now for 50 years, very successful theoretical framework known as the Standard Model. So that is traditional particle physics, both experiment and theoretical. But the sort of framework of this type of research is restricted by our current technological means. So, when you have a child and they have the curiosity, maybe a toddler, and you give them a toy, they throw it on the ground to see, how it breaks apart. That's what we do in particle physics. We throw things at each other to see what's inside.
Yeah, exactly.
The stronger you throw them at each other, the smaller the pieces that you will get, so you understand more fundamental things. So because of this, our current technology allows us to throw things at each other at a certain energy, but not beyond. So what traditional theoretical and experimental particle physics is, it's our understanding of the building blocks of everything, matter and energy, limited by what we've been able to discover by throwing things at each other at a certain energy, but not beyond that. So then the question arises, what happens if you throw things at even higher energy? We can't do it now. Maybe in the future we will do it. When you think of it this way, you realize that even though you can't do the experiments today, there are mathematical and logical restrictions of what the laws of nature could be for even smaller building blocks. So we're talking about atom. Within the atom, there's nuclei. Within the nuclei, there's quarks. We're talking way beyond that. What's inside quarks themselves? What's inside the electron itself? So there, you have to use imagination, mathematics, and logical consistency checks to see what the world might look like if you were able to do this experiment. Can you make predictions from now? And in some sense, it is an exercise in imagination, but it's also very important because history of physics has shown that when you push the envelope beyond what you're able to do in the laboratory, it can lead to revolutionary changes of how you think about the world. So string theory falls in that category. It's an effort to sort of push the envelope and say, what is everything made of at the most fundamental level? If we were able to throw things at each other at the highest possible energy, what would we discover inside everything?
Is that a string that we will discover there?
Yes. The suggestion of string theory is that, and the reason it's called string theory, is that when you do this thought experiment, you say, what does logic, mathematics, and some basic assumptions tell us about what is the smallest things from which you can build things? Then, interestingly enough, you end up with sort of a suggestion that things are made of strings, but not only strings. It's more complicated than that. But strings do play a critical role in the picture. So instead of thinking about things being built out of point particles, like the electron is just a point in space, you realize that you do need to entertain substructure of matter and energy, which is not a point, but it could be like a tiny string.
Why? I mean, a string is made of points.
It's a good question. So the reason the string arises naturally is because if you're looking for a theory of understanding nature at the most fundamental level, meaning that you want a theory that predicts everything. What do I mean by that? That can tell you that there must be an electron, that there must be a quark, and not only that, it must tell you what should the mass of the electron be, what should be its properties. So you have to even predict that and not assume that it exists. So that means that you have a theory where there's very little input into it. So generally speaking, when you have any science theory, you have a box which describes the logic, and there's some input you put in, and you can make predictions. And then you can compare the predictions with experiment. Now, if your box is supposed to be the most fundamental description of nature, then it should not have any input in it. Because as soon as you have input into the box, you ask yourself, well, where did that input come from? So there must be something even more fundamental you missed.
Okay.
So because of this, when you talk about string theory, you have to, from the outset, make an assumption that what we say in physical terms, there are no scales in the theory, meaning that there are no numbers that we need to measure and put in the theory to be able to use it. For example, to contrast it with the standard model, which is used in experimental theoretical particle physics, the standard model has depending how you count, 15 to 17 numbers that you have to put into it to make any predictions. For example, you have to measure the mass of the electron and then take this mass and plug it into the box that is the standard model before you can make any predictions about experiment. So what this tells you is that the standard model is not fundamental, because who gave you that mass? From where did you get? String theory is being fundamental should tell you that input, should tell you what is the mass of the electron in the standard model. But if you have that premise that you want a fundamental theory without any input, that any numbers that you have to measure, but you still can predict everything, then that is such a powerful constraint that it puts mathematical restrictions on what equations you can write down, because these equations cannot have numbers from outside in them. Everything should come out of them. And this is the origin of why the string becomes a special object, because mathematically, objects or theories which are two-dimensional, which is what a string is, then these objects have properties of not needing numbers from outside.
So is today's string theory able to really predict and explain everything in our world?
This is a very, very good question. So the short answer is no. And this is why string theory can also be controversial. Because you could say to yourself, what are you talking about? If it's not connected to reality by some predictions that you can check, then it's all empty. Physics is an experimental science. At the end of the day, the experiment rules. Yes. That's what tells you what is good and what is not good. And that connection today does not exist in string theory. It's more an exercise in what is possible beyond our technological means without the constraints that you get from experiments. And it could very well be wrong, and it could also be partly wrong. It could be that some of the ideas you entertained end up being correct. Now, this exercise of doing this is still extremely important. And the way I can describe this is with an analogy. Let's say you have a room which is very dark and you're trapped in it. And there's a door and you're trying to find the door. So one approach is you go walk toward the wall, touch it, and move around slowly by touching step by step until you come across the door. That could take a long time, of course, right? If the room is very big, it might take a very long time until you find the door. So imagine this room is nature, our world that we live in, and you're trying to understand it. So another approach, equivalent, is to walk randomly in a given direction, hit a wall. If it's not the door, turn around and walk in a different random direction. You will still discover the room, but it will be more adventurous because you really don't know every step from the previous one. So when you do exercises in theoretical physics which are based on imagination and logical constraint, you're doing these random walks. And many of the times, you're going to hit the wall. But occasionally, you're going to hit the door, and you're going to jump centuries ahead instead of going step by step. So this is also what has happened in history of physics. For example, the theory of general relativity, which describes gravity as we know it today through the curvature of space and time. So that theory, when it was written down, was not needed experimentally. There was no reason for it to write down this sort of description of gravity. Gravity, as it was described for centuries, was fine. Newtonian gravity, you had to do small tweaks, but that was it. So what general relativity did was take a century leap by thinking more imaginatively in sort of abstract way. That's an example of physics producing a big jump by thinking about things not in terms of what is the next experiment I can do, but what is perhaps the next experiment I can do in 100 years. Now, of course, in the case of general relativity, once the theory was written down, we could immediately test it because we knew what to look for. In string theory, there are no predictions yet. It's still a work in progress. There are no solid predictions that we can make and test it immediately. What there are indirect consistency checks. So the current laws of physics that we know and test regularly have some inconsistencies in them. So when you think about these inconsistencies, but you say, oh, perhaps what the inconsistencies are about is because we don't understand things properly. Maybe we use string theory to see how these inconsistencies are resolved. You find a lot of these inconsistencies are resolved. So this is sort of circumstantial evidence. So it doesn't mean the theory is correct, but it sort of means that some of the ideas you have is probably right. How they fit together in the big picture, we don't know yet.
The room you were talking about, if we examine this room step by step, we could still find, do the discoveries that you were talking about, but we could find other things too, like make other discoveries that we will not make if we just walk towards any random direction and then back and so on. Can we even use this step-by-step examination method in real science, in real physics?
I think that's a very good question. I think both approaches for discovery in physics and science as well should happen in parallel. So you need systematic experiments which push the envelope year by year, build in particle physics a bigger accelerator and throw things at each other with a little bit more energy and see if you discover something new. This is costly, it takes time, but it should be done because, as you said, in this process, you will discover possibly side things, including technological advances. For example, the Large Hadron Collider that is now currently the most powerful accelerator that is used in particle physics is the ultimate technological achievement of mankind, meaning that a lot of the technology that goes in it is actually the origin of other things that we use daily today. So this approach based on systematic experiments have many benefits and should be continuously done, and it's done. But it's also important to have a few crazy people thinking crazily just in case you make a huge jump. And so both in parallel is the discovery process of the world we live in. So string theory is of the second kind. It's speculative. We should be very careful about trusting it until there's experimental checks. But history has shown that we should continue thinking in sort of imaginative and crazy ways because nature has surprised us with very, very crazy ways of working.
Does today's string theory predict and explain the existence of atoms, neurons?
So here's where we are, and this sort of gets into philosophical questions. So since you are dealing with a theory which is supposedly what we call the theory of everything, meaning the most fundamental description of the natural laws. It has no input parameters, and it's supposed to predict everything. What we have discovered is, I'm going to sort of oversimplify it and give a cartoon of this, but the essence is going to be correct. So let's say you get the theory described by one big equation. This equation is supposed to predict everything, including you and me, all atoms and whatever happens. And there are aspects of string theory which can be written in sort of a grand equation like that. So there is actually a huge progress in this. So there are equations that we have that could describe the world we live in. They're extremely difficult to solve. So you have the logic there, but what word it leads to is difficult to get. Yet it can be done. In the last years, there have been progress in either numerical, computational methods to solve complex systems and start to understand, where does this lead to. So let's say you want to use string theory to predict that there is an electron. And what does that mean? You predict that there is some sort of particle that can appear to you, which has a certain mass, it has a certain spin and certain charge and properties. All this, the theory should be able to predict. Okay? So let's say you use these equations to predict this. What do you find? So again, in a cartoonish way, you do this exercise and you find, well, yeah, it does predict the electron, but maybe the mass that you predict is 2 times bigger than what it should be. So that doesn't look right. But then you suddenly realize these equations are so complex that they don't have one solution. You can find a solution consistent with these equations which predict another electron, possibly, whose mass is maybe only 10% different from what we measure. So that's interesting. And then you look at the equation again and you notice, wait a second, there's more solutions. There's 10,000, a billion, 10 to the 10. Each one of these describes a universe that is possible according to string theory.
How can it have several or even more solutions if there aren't different, input numbers or something?
Actually, there is an analogy that you can make from high school mathematics. I don't know if I'm going to get too technical, but there is in high school sometimes we learn about the quadratic equation. The quadratic equation is an equation that you solve and you get 2 solutions. It's one equation and it's set, but when you solve it, you get not one solution, but 2 solutions. And then similarly, in basic mathematics that we see in high school, we have this situation already. In string theory, it's that multiplied by much more complexity. So in a sense, it's not surprising if you're trying to describe everything that you ended up with an equation that has a lot of possibilities for the universe. In each universe, there will be an electron, but that electron will have different masses depending on which solution you look at. So then the question becomes, which one is our universe and why? So this is where it starts becoming philosophical. So I'll give you another story that illustrates how this happens. So this is an old, meaning 20-plus-year-old, a simplified picture which I'm going to modify for the case that we're talking about. It's called the fish in the pond story. So imagine that there is a pond somewhere, maybe it's Lake Sevan. And in this pond, there lives a fish, a species of fish. Maybe it's Ishkanatsuk. And I don't know about the details of Ishkanatsuk, but let's say this fish thrives when the water temperature is 15 degrees Celsius. If it's too hot beyond that, it doesn't survive. If it's too cold, it doesn't survive. So imagine now millions of years pass and these fish evolve. Ishkanatsuk start becoming smarter and smarter, and then they become sentient one day. So just like us, they start asking questions. Where are we? They start having kingdoms. They have their own Dirtat Takavor or whatever. And they start doing science. They have experimental physicists and who start observing the water they're in. You know, their word is this water, right? And one day, one of them invents a thermometer and takes the temperature of the water and says it's 15 degrees Celsius. Now, all the fish start thinking, wait a second, this is interesting. Why is it 15 degrees? Can we have a fundamental theory, maybe we call it string theory, which if we solve, we will predict that the temperature of the water must be 15 degrees, just like the mass of the electron in our universe. Mm-hmm. Now, if you're looking at this standing outside the pond and watching this happen, you realize that the question these fish are asking is stupid. There's nothing special about 15 degrees. There's nothing fundamental about it. The only reason it's 15 degrees is because the fish won't be around otherwise to ask the question.
Yes.
So this is perhaps what we are being driven to in this exercise of string theory, the realization that there are some fundamental questions which will not have a fundamental answer, because our existence has selected a universe where if things were very different, we won't be even around to ask those questions. So that's the idea of the multiverse, that a fundamental theory may be able to predict everything, but it would also predict many everythings, many possible universes. And which one we're in, it's a question of maybe biology that otherwise we would not be around to ask these questions. If that's the case, that means there are some questions that we will not find the answer of.
Because we're looking from inside the pond.
Yeah, because we're in the pond, so our ability to observe the world in it, we're in, is affected by the fact that we're creatures of a certain kind. It's affected by the fact that the mass of the electron or of the quarks have to be just right so that you have atoms, and these atoms can form molecules, and then these molecules can form organic molecules, and then animals and people. So then you're never going to be able to write a fundamental theory that predicts everything, because you will need the input in it of you who is asking the question.
Well, this is so much to understand and consider.
It's an interesting proposition. It's often referred to as the anthropic principle. And what is interesting is that this exercise or thought experiments that string theory forces us to do is, before we get to experimental checks, it's leading us towards some profound questions. And now, is this the only outcome? It's not necessarily true, because there are other ways that we can still ask fundamental questions and expect answers. I give you an example. Imagine that the universe we're living in is not special because we're living in, but it's the exact opposite. It's very average. So let me put it in a different way. So the problem with the anthropic principle is that at least the problem that I, for example, personally have with it, is that you're saying that there are some questions that are fundamental, like, for example, the mass of the electron or the mass of vacuum energy in the universe, which you will not be able to find a fundamental answer to. So don't even ask it. And why? Because these numbers that we measure are special because we're in it. So this is a special place. The problem with this approach is that we've been there before. We've been there in history where we thought the Earth was at the center of things and we're very special. And then later we discovered, you know what, we're not special at all. It's just one of billions of stars. It's actually a pretty typical star. Now we know there's lots of planets. Probably there are billions of planets much like Earth. So the story of science is always telling us you might want to think that you're special, but you're actually pretty average. There's nothing special. And it could be that we're also here seeing the same thing. There may be many universes, and we're in one of them. And that universe is not special because in the other universes, there are also creatures who ask the same questions, and they're more or less average. They're the same. So maybe we cannot predict the exact mass of the electron, and we will not be able to do, but we might be able to predict what is the average mass of an electron in a whole chunk of different universes, and that will agree pretty well with what we measure, confirming that we're average. That would be science, because in science often it's not about an exact prediction, but you do often statistical predictions. Like even when you take the temperature in this room, you're measuring an average quantity of a complex system, the average kinetic energy. So you still can make predictions about the system. So the same way, it could very well be that there is still fundamental science to be done, but you have to think of it in a different way, in a statistical way.
The multiverse you mentioned, how does string theory explain it? What does it look like, if we can say so, according to the string theory? Does it have anything to do with Marvel's multiverse?
I think I don't know about I haven't followed the Marvel sequence, but I think when you look at the universes in the multiverse that string theory predicts, you find things all over the place. There are all kinds of different universes that can happen. There are universes that you can find which are, like, for example, how is our universe here today that we see? We see a chunk of space with some matter in it, and then the whole cosmos is expanding. So there's the Big Bang, and then from that we have an expansion. So when you look at different possibilities according to string theory of different universes that are still possible according to the fundamental equations of string theory, then you find some universes may not be expanding or maybe expanding slower. Some of them may be collapsing. So you find all kinds of things. You find some universes may not look three-dimensional, but could be 5, 6-dimensional. So you get a bit of everything, a lot of crazy. These are all possible outcomes. We just happen to be in one that has 3 dimensions and space expanding just right. And what is sort of interesting about this is that when you look at our universe and you look at the observational cosmological data, you do see some curious accidents in the numbers we measure. There seems to be a certain special thing happening as far as what we see in the universe today. So we don't understand it. So I cannot say where it will lead to. String theory will not answer these questions at this stage. But there's something very interesting in cosmology that we're starting to see. And this sort of brings back to the original question you were asking, which is, how do you get this theory to connect to reality and do experiments with it? I think the framework of string theory to be tested, whether part of it is correct or all of it is correct, is something that is unlikely to be tested in accelerator physics. So these big instruments that we're building are technologically, at this stage, too far off to be able to test string theory. However, in the last decade or so, we are entering what I would call the golden age of observational cosmology. So we are discovering imaging black holes, which were never sort of realized before experimentally. We are measuring attributes of the cosmos, including the rate at which it's expanding, at less than 1% accuracy. So we're starting to see gravitational waves, which is a very powerful way of seeing the universe that was never possible before. So I think in the next decades or century, looking deep into space is where the big secrets will come out, and might be a place where string theory could be put to a stress test and see how much of it is right.
Does string theory explain how a multiverse can even exist? How did it start, if we can say so?
Yeah, in principle, the theory is and should be capable to explain both the beginning and the end of any of the universes in a multiverse. So there are technical problems in solving these equations because they're very complicated, and there are places where, more work is needed. But in principle, if we had infinite power and charisma and we could just solve everything mathematically that the theory tells us, it should be able to answer any of the questions, including how a universe starts and ends, etc.
Could be, but is not explaining, we cannot explain it at the moment.
Yes, part of the challenge is that, so there's two challenges. One challenge is that you have a theory that's telling you many universes are possible, and it can't tell you why you're living in the one you're living. And so that relates to the anthropic principle. But there's an additional problem that within each universe, your ability to compute predictions is technically difficult. It doesn't mean it's not possible, but it means it's a lot of work. And if you have billions of universes, then it becomes even more complicated. So it's a compound problem. It's not just about being able to compute, but also even if you're able to compute, you don't have enough information to tell why we live in the universe that we live in.
Well, it cannot explain why we live there, but, how do I put this? Does it explain why do we even have a multiverse? If we do, how did they appear, if we can say so? And how does this work with the Big Bang theory, if you know what I mean? Big Bang explains that there was a Big Bang and the universe appeared. So did a multiverse appear at that moment? Or did
Yeah, this is a very good question. There's all kinds of layers to it. First of all, within each universe as a possibility from string theory, you can, in principle again, use string theory to track the evolution of the universe through its big bang and expansion and collapse or whatever as a function of time. So that's part of the sort of capability that the theory should have. But there are also interesting things happen because this picture of multiverse, it does not mean you have a bunch of parallel universes, sometimes they're called, only, meaning that you have one scenario, another scenario, and we're in this scenario. And within this scenario, string theory will tell you this is how things begin and this is how things end, including Big Bang. So within this sort of universe, you should be able to find the evolution of how things are moving forward and backward. But in addition, there is the logical and maybe even likely possibility where you can have universes within the same space. So you could have a region which looks like the universe we live in, and then there's another universe somewhere else which is potentially accessible, where things look a bit different. I can tell you a scenario that's been understood now, which sort of, again, falls in the category of circumstantial evidence. So you can imagine in string theory that a universe that we live in is like a sheet of paper. So imagine there's a sheet of paper and we're stuck to it. Mm-hmm. We're on it. So our universe, everything we see is this sheet of paper. Now the sheet of paper is two-dimensional, right? Our universe is three. So it's a cartoon, it's not an exact. But imagine you have this sheet of paper that is our universe. And you can realize this in string theory. You can realize a universe that looks like ours, more or less, that appears in the big picture as something that lives on a subset of space or a sheet of paper. Now imagine you have another universe, that's another sheet of paper. Mm-hmm. And you have yet another one, so you have billions of them. Each one of them is a universe with its own history and fish in it, okay? So now you can do some computations in string theory to see how these universes talk to each other, how can they interact. And one thing you can do is you say, what if you have two of these universes, these two sheets of paper, and they can move around in a bigger space? What if they are moving toward each other? They're going to collide. If you're on one of the universe, can you tell that another universe is about to collide with you? Is there something you can do to tell that even though you're on the sheet, there's another universe in the multiverse that is coming toward you, eventually will collide with you?
Can they even collide if they are like in different levels?
String theory predicts that these interactions can happen, and it can actually compute the probability. We can compute also how the universe on one sheet of paper will look like because another universe is on a collision course. And here's what one discovers. One discovers that pretty generically, string theory would predict that on one of the sheet, which is on a collision course with another universe, you see your universe expand, which is what we see. So then you could say that the reason that we have Big Bang and the expansion of the universe that we can observe today experimentally, if we ask why, what you just asked, why is there a Big Bang? Why this thing? Why is the universe expanding? Then one answer string theory can give you, well, we are on a collision course with another universe. If that's the case, string theory would predict an expanding universe. Now, that doesn't mean that we proved that string theory is right, but it's circumstantial evidence that shows, some of the things that are open questions within the physics that we can test today have interesting answers in this framework that is called string theory. Interesting answers that are even perhaps plausible. Now, of course, what you want to do then, you want to say, okay, if that's the case, what else does string theory predict about your universe that we haven't discovered yet in cosmology, but perhaps we will discover in the next decade. And it adds another piece of evidence. So now you have multiple pieces of evidence. You start thinking, oh, maybe we're getting something right.
So are there any other interesting predictions?
Yeah, there are all kinds. There's also predictions that we don't see. For example, string theory necessitates, for logical consistency, there must be certain symmetries in nature. You know, one of the things that is very beautiful about physics, you know, something is beautiful when there's a lot of complexity that comes from it, but it's at its core very simple, where it's very frugal. And so physics has that in it, where there are a few ideas which are key, and then from it everything else arises. And so the general scheme that you see in physics is that what we're doing for the last centuries is we're cataloging the symmetries of nature. That's what physics is. So I can tell you a story which I tell my student about the beginning of physics. And that's the story of the first two physicists, Tycho Brahe and Johannes Kepler. So Tycho Brahe is the first experimental physicist, and Johannes Kepler is the first theoretical physicist, and Newton came after them. And so they had a very interesting relationship. Tycho Brahe was always drunk, and he eventually died from over-drinking. Johannes Kepler was very poor, and he actually died in a refugee camp. But in between, they met each other. And that's how physics started. So Tycho Brahe was building with his own money, he was very rich, telescope to look into the heavens and recorded the positions of the stars and planets. And then Johannes Kepler looked at these numbers and saw patterns in them. He noticed that something is remaining the same. That's symmetry. So what we do in physics is always the same. We look at things, measure, write numbers, then we draw graphs or tables to find what's the pattern in it. Sometimes the pattern is very complex, but you can unravel it if you look at it differently. And when you're looking at the pattern, like the patterns that we have in Armenian culture, you know, on dresses, these have symmetry structures in it which govern them. So physics, in a nutshell, is cataloging the symmetries of nature. Everything we do in physics is just that. So string theory, in the same spirit, is a catalog of symmetries we know, but also symmetries that we propose exist from all kinds of logical, but also some mathematical considerations. So one of these symmetries, called supersymmetry, is necessary for string theory to make sense. We have no evidence of it in nature. We don't see it anywhere in the particle physics, I should say. Does this mean string theory is not correct? No, because there are ways where you can have a symmetry that does not appear. We know cases in physics that happens. So perhaps that's what's happening. So things look more complex than they actually are. So when you say about, I forgot the original question, but I sort of wanted to underscore that a theory like string theory can make predictions. Some of the predictions look very interesting and explain some things we see, at least indirectly, in cosmology. But it also has some predictions that we don't see, and we don't fully understand why we don't see. So this is why it's speculative. It's an exercise which is still abstract, and that hard connection hasn't been made yet with the real world.
This topic is endless actually, and I hope we will get back to it one day, perhaps very soon enough, but I guess this is all for today, and thank you a lot for coming here.
My pleasure. Thank you for inviting me.